The final topic of Module 11 is antiderivatives with so-called initial value condition. This is particularly important in an institution which are heavily geared toward engineering. But in UNT Dallas, we put only a moderate amount of attention here. That's why it is buried as section 4 here. Please recall that antiderivatives are not unique, so if you take the antiderivative, you have plus c. But with additional condition, we can determine this plus c. Here are some examples. Capital F prime is 2x, alright, but let's put additional condition. F of 0 is 0. In that case, you have to have only this function. F of x, capital F of x is x squared, nothing else. Please check. Plug in x equal to 0, then we have 0. With this condition, capital F of 0 is negative 1, we have to have this function only. Please check. Plug in x equal to 0, then this one becomes 0, and we get negative 1 indeed. How about this condition? Capital F of negative 1 is 3, for example. In that case, we have to have this kind of function only. X squared plus 3. Please check. Plug in x equal to negative 1. What do you get? You get capital F of negative 1 is equal to 3 with this thing. These kind of things are called initial value condition, or just initial condition for simplicity. And these are now the antiderivatives because now they are unique. The finding the antiderivative under appropriate initial value condition is called initial value problem. And then let's discuss some of those problems here. All we have to do is calculate the antiderivative and then do some algebra to find out c value. Here we go. Let's find out small f of x using this integrand and the IVC, initial value condition. Here we go. First, let's calculate the antiderivative. Piece of cake. Just power functions. Alright, go ahead. Easy, isn't it? This is just x to the 1/2 power. Okay, here we go. And now, let's determine the constant c through the initial condition. We are plugging x equals to 1. Then this is what we get. If you plug in x equals to 1, x equals 1 here, the value has to be 1/3. You see, the problem said 1/3. So this has to be 1/3. And what's this? This becomes an equation of c. Very easy equation of c. A little bit of computation, we are going to get negative 4/3. Alright, we found out c value. Let's put everything together and you can find out the antiderivative function. This one, and then instead of plus c, we have minus 4/3. Here we go. The final answer. The antiderivative function under the initial value condition. One more exercise. We have this antiderivative computation to do, and then we are going to put this initial value, put x equals 1/2, and then the function value has to be 1/2. Okay, let's calculate the antiderivative. Okay. Oh, we should have reviewed this kind of antiderivative a little bit more. Maybe this is a good time to do that. Alright, let's do it. Let's do antiderivative computation for something like this one. How do you handle that? Well, please note that this is a power function. You see, don't look at it as a reciprocal function and then imagine log function in there. I gave you antiderivative formulas like this. K power, then we have this. -1 power, then log. So, actually this is better. K power, then we get that. -1 power is this. not just 1 over x function. That'll help. This, you can change it into power form like this. 2x plus 3 to the what power? Negative of 1/2 power. Why negative? That's because this expression is in denominator. Why 1/2? That's because this is square root. Radical is fractional power and denominator is negative power. Okay, let's apply the power rule. 2x plus 3. Raise the power by 1, so add 1, and then divide. Is that it? No, not really. One more to go. We need 1 over a. This 2 and that 2 came from different origin. This 2 down here, which I'm emphasizing different color, came from this 2. Okay, how about the exponential part? See, the same, but we need this 1 over a. This 2 came from this 2. Okay, and then plus c. There goes my antiderivative computation. Well, here I did some further simplification, changing it back to square root expression. Okay, it's a bit of simplification, so I can do that. Anyway, there's no reason to keep duplicate solutions, so here's one. Now we're going to use IVC to determine c. We're going to plug in x equals 1/2 and put this expression equals 1/2. We can solve for c. Here we go. Plug in x equals 1/2. What happens here? Plug in, so this is 2 times 1/2. Okay, alright. 2 times 1/2 plus 3. So this thing is square root of 4, so it became 2. And how about this one? Okay, this one is 2 times 1/2 minus 1, so it becomes e to the 0 power. So in the end, what do you get? 2 minus 1/2 plus c. That's equals 1/2. It's an easy equation to solve. So for c, I get c equals to -1. So what's the conclusion? C value is -1, so plug it in, and I'm going to get the final answer like this. This kind of problem is called the initial value problem. And let's see, among higher level math courses, differential equation requires this. Among physics and engineering, just about everything, general physics and on, just about everything requires this. Here in UNT Dallas, I'm not going to put too much emphasis on these kind of problems. But I have written this kind of problem in the exam, so here we go. Okay, just a little bit further initial value problem. How about something like this? And this is pretty much the same as the previous problem. I'll leave this to students. Something like this. A little bit harder because this time you have to use antiderivative twice. You see, you have second derivative. So take antiderivative once, you get c. Take antiderivative again, you get another constant, say c1 and c2. So we need 2 equations for 2 unknowns. That's why we need 2 initial conditions. Ready? Okay, here we go. Antiderivatives. X double prime to x prime. Here we go. We take the antiderivative. X prime to x. We take the antiderivative again. Here we go. Luckily, antiderivative computation themselves are easy. Cosine becomes sine. Sine becomes negative cosine. Sine becomes negative cosine. Negative cosine becomes negative sine. And then, tricky part, the c becomes c times t. Okay, we have these two constants c and d to determine, and we have these two conditions. Plug in x equal to 0 to this thing, plug in x prime equals to 0 into this one here. Excuse me, not x equal to 0, t equals to 0. Okay, ready for initial conditions? Let's go. Plug in t equals to 0 to this thing over here. What happens here? In this function, x prime. Oh, let me see. Excuse me, I did this one first. Okay, either way it will work. Plug in t equal to 0 to this one. What do you get? Cosine of 0 is negative. Excuse me, cosine of 0 is 1. So this is just negative 2. Sine of 0 is 0, so this one disappears. And plug in t equals to 0, so this 2 disappears. And what do you get? Negative 2 plus d is equal to negative 3. You can determine d from this. D is equal to negative 1. So this one over here is equal to negative 1. Next, let's plug in t equal to 0 to this one using the second condition here. Alright, plug it in. Sine of 0 is 0, so this one disappears. Cosine of 0 is 1, so we get negative 3 plus c is equal to 1. And from here, let's find c value. Turned out c equal to 4. Plug in over here, and I'm going to get the final answer. This is a conclusion. C is 4, D is negative 1. See? Here is the full solution. So it is possible to use initial value condition twice. If you have to take the it's possible to take, let's see, even if you have second derivative, and even if you have to take the antiderivative twice, it is possible to determine the antiderivative if you have two initial conditions. This, by the way, is very, very useful and important in physics. This one is related to harmonic oscillation, and this one is initial position of that oscillator, and this one is initial velocity of that oscillator. And let's see, Newton's equation of motion requires second derivative. So this kind of thing, second derivative is given as a certain function, and then we need two antiderivative computations and two initial conditions to determine two integral conditions. Those kind of things are really, really common in physics and engineering. Now, do we have enough time for an extra topic, a boundary value problem? Okay, let's talk about it. I de-emphasize in gray because this is kind of different, but let's talk about it anyway. Okay, and for simplicity, I took the same problem, same antiderivative, so that we get same antiderivative computation. Let me open up the previous problem here. The same thing, right? Instead of this initial value condition at same t value, I took two different t values but two different x values, x of 0, x of pi, and traditionally these kind of things are called boundary value problems, and usually it's valid for t value between 0 and pi, but necessarily it can go beyond. In this particular case, it can go beyond. So how does it work? The same. Take the antiderivative twice. The same computation as before. And then put boundary condition twice. Plug in t equal to 0 to this, t equals to pi to that. And here we go. Plug in t equal to 0 to this. The same computation as before. Sine of 0 is 0. Times 0, so these two disappear. Cosine of 0 is 1, so you get negative 2 plus d. And this is given as negative 3, so we get this equation. And you get d equals to negative 1. Simple computation. Next, plug in t equals to pi, and here we go. Plug in pi. Cosine of pi is negative 1, so this is positive 2. Sine of pi is 0, so that disappears. And pi times c, that doesn't go down to 0. D is equal to -1, as we saw in the previous part. So you can solve for c, which is in this case -2 over pi. Just an easy equation to solve. So we get c value and we get d value, put everything together, and we have the antiderivative function. This kind of problem is called a boundary value problem. A little bit advanced, but here we go.